Hi, my name is Greta Shum, and I'm going to be sharing with you some research that I've done about the relationship between expansion of forest, consequent changes in the atmosphere, and what that means for plants nearby. I'm going to be discussing this work that I've done with my advisor, Dr. Abigail Swann at the University of Washington in Seattle, and Dr. Marysa M Laguë at UC Berkeley. So let's get started. So we know that the Earth experienced a relatively warm period around 6,000 years ago, which we call the mid-Holocene. And we know that that's primarily due to differences between modern orbital configurations and mid-Holocene orbital configuration. And I'm showing you here a figure from the IPCC that has data on the top. So each point is a data point based on pollen reconstructions of temperature. And I'm specifically showing you the mean temperature of the warmest month. And if it's blue, that means the mid-Holocene record was cooler than modern. And if it's red or orange, that means it was warmer. Then below, I'm showing you output from an intercomparison group that looked to recreate this data. So again, this mean temperature, the warmest month. And you can see that there's a lot of uniform warming, especially in the northern hemisphere, that's consistent with the differences in orbital configuration. But the story is not really the same as the data show, especially if you look in the boreal northern North America there. And the idea here is to look at what kind of feedbacks could have been causing this heterogeneity. So just to remind you, we know that the atmosphere can affect vegetation on the ground by modifying its growth or carbon uptake. So that means that when the atmosphere does something, the vegetation sits up and listens. But we also now know that when vegetation does something on the ground, the atmosphere also reacts, and that's true for global climate model simulations and in observations. And what we now know is that uncertainties in how much the vegetation will react to any given atmospheric change feeds back into uncertainties in climate projections. So this has been shown to be true in CMIP5 climate projections as well as CMIP6. And actually, Foley et al. In 1994 showed in an experiment where they took the vegetation distribution of the boreal forest and pushed it northward to recreate what was going on during the mid-Holocene, that feedbacks from vegetation actually had about the same magnitude as warming caused by orbital forcing during this time. And you can see that there's even a seasonal nuance here. So springtime warming was actually found mostly due to trees, while summer and fall and warming was mostly due to orbital changes. And if we look more closely at these changes in vegetation distributions that were going on during the mid-Holocene, you can see I'm showing you here a time series from 10,000 years ago to modern. And you can see the Laurentide Ice Sheet, that blue blob, goes ahead and shrinks over the course of time. And if we zero in on mid-Holocene time between like 7,000 years ago and 5,000 years ago, you can see that this boreal needleleaf evergreen forest emerges right behind it, and you can see it becomes really, really densely packed forest right during that time. Strong emergence of forest. And I guess the question we want to ask here is, could that land surface interaction have driven forest expansion and warming during this time? So think of it as maybe a forest self-perpetuating into expansion, so self-perpetuated ecosystem expansion via the climate, or a little forest spree. So you can actually use a global climate model to simulate the expansion of forest in this incremental way. And that's actually what we did. We did a two-phase experimental setup, and I'm going to go through that right now in order to tease apart these vegetation, atmosphere, and then back to vegetation interactions. So phase one consisted of a set of interactive or coupled global climate model simulations. And we actually used the Community Earth System model, version 5 for the land model and version 6 for the atmosphere model. Now you can see here I'm showing you on the left with these two interactive arrows that we had an atmosphere interacting with the land, and the difference between these two experiments was that in the control we had bare ground on the surface of the Earth, and that just means dirt. By contrast, the experiment had a block of forest, as you can see, needleleaf evergreen boreal trees. And these are trees, as you can see, sort of with the spray of green to the southeast that are natural to this area. And we also put in an ice sheet, which you can't quite see in the experimental control, but you can see in the difference plot there that we had an ice sheet where no vegetation could grow. We ran these simulations for 80 years and discarded the first 40 years as spin-up. So phase 2 consisted of a set of offline simulations using the output from that coupled experiment. So think of it as a time series of all those different atmospheric variables that we would apply to the land surface. But what we did with the land surface was different. We, instead of having that block of forest, wiped out the ice sheet as well and painted the entire Earth, all the land surface that could be covered with plants. We covered with plants with only one type of plant. And in this case, I'm showing you PFT2 or boreal needleleaf evergreen trees, which are the same kind of trees that we used to plant that forest. But we also did this with a total of 5 PFTs. So you can see that these are all plant functional types that are relevant to this region. And so the idea here was to apply the atmospheres from the 2 different initial simulations to those offline land models and not allow them to react to the atmosphere, but to see what the influence would be of that forested atmosphere versus the bare ground atmosphere. And again, we ran these simulations for a total of 80 years, but we actually just took those last 40 years of the coupled simulation and applied them twice. And again, we threw out the first 40 years. So this is our experimental setup, and it's meant to investigate the question of what the influence of the forest would be on the atmosphere in a way that's relevant to plants nearby. So I'm actually just going to jump to the end of the story here and answer the question, what happened to the plants? How did they do in the end? And I first just want you to think about what you would expect to happen given this experimental setup. And I'm just focusing on outside of the region of the vegetation, of the planted forest. So if you were a plant outside of that region, do you think that you would do better or worse when exposed to an atmosphere that had the fingerprint of a forest or the fingerprint of bare ground? And if you think that there would be a difference at all, where do you think that that would be the largest? So I'm going to give away the answer here, and I'm just going to show you one example of one plant functional type, one PFT, and that is the broadleaf deciduous boreal shrub. And you can see here that the green is meaning that the plants actually did better in the atmosphere exposed to forest, whereas brown would mean that they did worse. And again, this is just one of the plant functional types that we tested. Now I'm going to show you all of them. This is the one that I just showed you for the springtime productivity change and the summertime productivity change. So here we go. And what you can see if you just glance at each one of these plots is that a lot of the growth activity, or the difference in growth, is to the south and west of the planted forest. And you can see that mostly it's positive. It's an increase in growth when you go from bare ground to forest. But you do have a little bit of decrease in growth. So if we just zero in on this one, this needleleaf deciduous boreal tree, you can see that in the springtime we have increase in growth in the west of the vegetation change and then increase in growth to the south. So we kind of picked apart those 2 areas of change. And for the purposes of this talk, I'm just going to focus right now on the south box there, just with the land units there that did better. And they did better all year long. So here I'm showing you a time series from January to December of the change in gross primary productivity, GPP, over the course of the year. And you can see that the 0 line is all the way at the bottom there, and not at any point does the mean increase in GPP go below 0. So that means that just across the board, the plants did better when exposed to an atmosphere that had the fingerprint of forest. And I've actually starred here the months where the change in GPP using a student's t-test had a p-value of less than 0.05. So what about the atmosphere change that the plants actually care about? The main thing that plants in this region care about when they're trying to grow is temperature. So let's look at what happened. All right, so if we just look at the left-hand side here, this is showing you the springtime change in near surface temperature, and by near surface I mean 1,000 hectopascals to 820 hectopascals. So that's pretty low near to the surface, and you can see that there's a lot of warming in the springtime, especially to the west of that planted forest. Then if we look at the summertime, that JJA months, we can see that the warming continues, but it's not as pronounced in the west, but we have still this warming in the time of year when the plants are growing. Whereas to the east of that planted forest, we actually see cooling, so that might be a reason why the plants didn't enjoy growing over there. So what else do the plants care about? The other thing that plants care about in this region is sunlight. So how much sun is reaching the surface and actually getting absorbed. While we didn't change the surface albedo of the area outside of that vegetation box, you may remember that the main thing that we changed in the coupled experiment was this change in the surface albedo. However, outside of the box, if we just focus on outside of that vegetation change, the main thing that's going to be tempering the amount of sunlight that these plants are going to see is cloud cover. So let's look at clouds. I'm showing you here a fraction of low clouds, and those are the clouds that are actually going to be reflecting the most shortwave radiation or solar radiation. And you can see that to the south and west in the springtime, we actually see a reduction of clouds. So green means that you see fewer clouds when exposed to a forested atmosphere as opposed to a bare ground exposed atmosphere. Then if we move to the summertime, the same is true. We actually see an increase in clouds to the east of the planted forest. So if we take a look at the surface energy budget, and by that I mean the balance of radiation or energy received by the surface and then the output from the surface, this will give us an idea of what the plants are actually experiencing and doing on the ground. So this is the difference between shortwave radiation received when exposed to the forested atmosphere versus the bare ground atmosphere. And you can see that across all the growing months, which is spring to summer, you can see an increase in shortwave radiation received. And that's consistent with what we saw, where we saw a reduction in cloud cover. As a result, we see an increase in temperature and then a resultant increase in the outgoing long-wave radiation. So the surface is warm, and so it's radiating in long-wave radiation. We also saw that increase in gross primary productivity, and that's going to be shown as an increase in the release of latent heat flux, especially since you have an increase in total energy coming in, and that means evaporation and transpiration are going on here. And then finally, the sensible heat flux changes are going to be following sort of the trend here and acting as a bit of a residual. So what about where we actually planted the trees? So the change in the forest extent is going to be our main driver here of all these changes in the atmosphere that we're seeing. So what actually happened if we drill down and look there? So first I'm going to show you temperature, and what you see in the springtime is a dramatic rise in temperature from bare ground to forested atmospheres. In the spring you get a really large increase in warmth, and you can imagine that that would be because of an increase in albedo, and then a decrease in albedo there. And then in the summertime we have actually a lot of cooling as opposed to what we saw outside of the box, which was warming across these growing months. And why is that happening? So let's look at clouds again. So if you see the springtime, we actually have a similar decrease in clouds over the area, decrease in low clouds over the planted forest, but I'll tell you that actually overall we actually see a small increase in cloud cover. And then over in the summertime, we actually see an increase that's more pronounced in low clouds over that area of vegetation change. And that's in contrast to the decrease in clouds that we see outside the box. So if we take a look at this in the surface energy budget perspective, this is something that we can kind of see as familiar to us after looking at the Foley et al. Experiment. You see that the vegetation change is lowering the surface albedo. Like we said, we replaced bare ground with dark forest, and that shows that results in an increase in surface energy, or in shortwave received by the surface, and it also isn't hampered at this point by any change in cloud cover. Whereas in the summertime over this forested region, we actually saw an increase in cloud cover, so that means that the shortwave radiation wasn't even reaching the surface to have that change in surface albedo. So we also see a change in outgoing long-wave radiation that follows that pattern. So an increase in temperature would mean that you're radiating that radiation out from the surface in the springtime, whereas in the summertime you're actually having a cool surface, so that decreases the amount of radiation that you would have been putting out. And then of course we planted a giant forest, so are actually going to be allowing a lot of that increase in energy to be released in the form of evaporation and transpiration. But when you don't actually have an increase in total energy, it's actually going to change your partitioning of sensible heat flux in the opposite direction. So just to summarize, we have a warming during the springtime that's caused by a higher surface a higher amount of shortwave radiation because you have a lower surface albedo, whereas in the summertime when we had that increase in clouds, we actually have a cooling effect over the box of planted forest. So we have this mystery here of the two different things going on inside and outside the box. Why did the neighboring plants get warmer and less cloudy outside of the area of vegetation change? And in order to tease apart this question, we followed the example of the Kim et al. Paper in 2020 that looked at evaporative resistance versus albedo impacts on cloud cover. And you can see that they teased apart the changes in relative humidity, which they kind of used as a proxy for cloudiness, between the change that would have taken place as a result of a change in temperature and the change that would have taken place as a result of the change in specific humidity or moisture. So we did that same thing when we looked at what happened in the south box here. And the blue line is showing you the effect of temperature pulling relative humidity down, whereas an increase in moisture actually pulled that relative humidity up. So if you have a higher temperature, you can actually hold more water, so your saturation vapor pressure goes up. But that moisture increase in relative humidity was not enough to take care of the change that the temperature actually caused. So what we're seeing is that the temperature is really driving a decrease in cloud cover. And if we take a look at the mean winds, this can give us a clue then overlaying it with temperature here. This is showing the difference in mean winds over the difference in temperature. And you can kind of get an idea that maybe the warm blob over the forest during the springtime may have been a source for warmth, whereas the ocean may have been the source for warmth during the summertime here. Even though it may have been transporting in some moisture, we still got a reduction in clouds. So just to summarize everything, I just want to remind you that we saw an expansion of forest cover can make a more hospitable climate for neighboring plants, which is a mechanism that could potentially perpetuate self-expansion of the forest. And secondly, we saw that plants warm their local climate in the place where they are in the spring and cool their local climate in the summer by altering the cloud cover and surface albedo. And thirdly, we saw that plants can make neighboring climates more hospitable in the spring and in the summertime by increasing temperature and reducing low cloud cover. And with that, I'd just like to thank my collaborators and thank the AGU for allowing me to share this research with you all. And happy to take any questions.